field as well, an topic of interest to me, of course, and zonal flows. So we're going to try to keep things on schedule, of course, because there's a break and then discussions afterwards. But ask questions.
Thank you, Dr. Kato. And first of all, I would like to thank Alex for giving me a good opportunity to talk here about our recent study. And also thank you all of the audience for sitting here in the afternoon of last day. Okay, this work has been done in my colleagues Tomohiko Watanabe sitting here and Nunami also here. And this is the outline of my talk, but I'd like to change the order of these things because, and first I'd like to talk about momentum balance and radial electric field in quasi-symmetric system with stellar symmetry, because this morning Pahilanda's talk and also yesterday's talks about momentum transfer are very much related to this study. And now let's return to the basic Boltzmann kinetic equation for description of collisional turbulent transport. Here we assume equilibrium magnetic field forms a nested toroidal surface. Then, as you all know, so basic Boltzmann kinetic equation is given by this. Here, this hat symbols are representing fluctuation part, and variables without hat is ensemble average part. If we take ensemble average of this basic kinetic equation, we get this ensemble average kinetic equation. These variables without hat are ensemble average variables. Also here, in the right hand, we notice the correlation of fluctuating electromagnetic field and fluctuating distribution function appear. Now, classical, neoclassical, and anomalous transport of particles and heat are defined in this slide. Here, first, we use a gyro phase angle average in the velocity space, denoted by C. And then we define average gyro phase average part and oscillating part of orbital function f, and by this overline f and f tilde. Then particle flux and heat flux are defined by this definition. And here, this radial transport flux is only dependent on oscillatory part of distribution function. Now we divide original Boltzmann and kinetic equation into gyro phase average part and fluctuating oscillatory part in gyro phase. Here, this L operator is defined by phase space convection derivative with this first gyro oscillation part dropped. And as already well known, this particle, radial particle and heat flux are of second order in this delta. Delta representing the gyro, small gyro radius ordering parameter, often called by also rho star here, but we use delta. And then this particle flux, heat flux are non-vanishing only in second order, from second order. And then solving this, we can separate this second order distribution function dependent on gyro phase is divided this part, and corresponding these parts we can define substituting this into this definition of particle and heat flux. We can separately write this particle and heat flux as a sum of neoclassical, classical, and anomalous parts. These parts are coming from this contribution. First one is this orbit effects acting on gyro phase average distribution function, and the classical part is contributed from this collision term acting on gyro phase fluctuating distribution function, and this anomalous part is coming from this d tilde. D is defined in the previous slide in this correlation of turbulent electromagnetic and distribution function. Okay, and here we assume slow rotation ordering. So background E cross B flow is assumed to be thermal velocity multiplied by delta. Okay. Then, if we take the first moment in the velocity space of the original ensemble averaged kinetic equation, not this one, we can get the momentum balance equation like this. Here, N is ensemble averaged density, and Nu is particle flux of ensemble average distribution function. And also, in the same pressure tensor and friction force is all defined in terms of ensemble average average distribution function. Here, ensemble average distribution function is assumed to long scale length, like a machine equilibrium size, and also we employ the transport time scale ordering. So time variation of this ensemble average variables all depend time very slowly. Okay, and also this friction electromagnetic force term is also coming from this D. And if we use Maxwell equation, speed summation is also written by this form using turbulent electromagnetic magnetic stress tensor, and also this S representing turbulent electromagnetic pointing vector. Okay. Also, now we take the component of momentum balance in the direction tangential to the flux surface. And here C1 and C2 is orbitally constant. Then this equation is written by this expression. The left-hand side represents a time variation, temporal variation of momentum. Also, contribution from pointing vector also enters the left-hand side. These are components tangential to the flux surface. In the right-hand side, we can get this divergence term of pressure tensor and turbulent electromagnetic magnet stress tensor part. Also, here radial electro current appeared. Also, using Maxwell's equation, this radial electro current often written by this temporal variation of radial electric field. Okay. Now,
what was that last equation again?
This is just a radial electro current. Flux average radial electro current equals to using Maxwell equation, that is time derivative of radial electric field. Okay. This is often, but this term is usually much smaller than this term, polarization term. So often neglect. Okay. Now we consider quasi-symmetry. Dr. Helander gave a very nice introductory talk about quasi-symmetry. Here, quasi-symmetry is given by this condition. Again, C1, C2 are constant. And if we consider C1 equals 0 case, that is corresponding to the axisymmetric case. And if we put C2 equals 0, then that is quasi-polarized symmetry case. And as well known, so all the delta viscosity components are quasi-asymmetry direction vanishes. That is corresponding to the talk by Dr. Helander in this morning. And by partial integral, this tangential component of the pressure tensor is written by this. And if we assume this quasi-symmetry, that will vanish. So in this case, this first order term is vanished. Also, if we take the assume such a turbulent transport time scale ordering, this left hand side is third order in delta, then this is vanishing up to delta order. So that is corresponding to intrinsic ambipolarity in this order. Okay. Also, again, now another symmetry is considered often in symmetry stellarity system that is called stellarity symmetry. LHD also, when you say X is satisfied, this stellarity symmetry. Stellarity symmetry is defined like this. Consider this stellarity system. This system looks the same even after the 180 degree of rotation of some axis lying in the equatorial plane of toroidal system. And this case, magnetic field, if we take the origin of toroidal angle at this position, then this magnetic field strength as a function of the flux coordinate, this is the even function of toroidal and toroidal angles. Also, if we keep looking at this system, we noted these parities. Magnetic field components, some of them are having even parities, and this radial component has odd parity. Also, magnetic tensor components is also these parities. And if we have only odd number of toroidal angles in the subscript, that is always odd function of theta and zeta. Okay. And also, this G is determinant of this metric tensor component. Also, that is a symmetric function of theta and zeta. Okay. Now, we consider some parity transformation associated with stellarity symmetry. This symmetry only valid for the system with stellarity symmetry shown in the previous slide. Okay, here we introduce another expansion parameter eta here, written here, but that magnitude of order is completely the same as delta. And but this is used because of some definition of parity operator. Okay, and also in order to introduce such kind of ordering, we often put this electric charge replaced by this inverse eta E. Then that is naturally introduce such kind of kinetic ordering, small gyro ordering in the original equation. Please imagine here we put inverse eta here. Okay. Then the solution of this equation and Maxwell equation also considered as a function of eta explicitly too. And this is corresponding to such small gyro radius expansion of distribution function, also electrostatic potential. And lowest order of distribution function is assumed to be local Maxwellian and independent of toroidal angles. Also, that is slowly changing in time, and this is first order and second order. Also, if we assume slow rotation, electrostatic potential here is beginning from the first order in eta. Also, lowest order potential is assumed to be a function of S only, independent of toroidal and toroidal angles. Then, now we define important parity operator associated with stellarity symmetry by this orbital function of Q in the phase space and also having parameter eta. For this orbital function, we define this operator by this equation. That is changing the direction of toroidal angles and also velocity component, toroidal component of velocity. Also, we put the opposite sign to the original eta. Okay. Then input, yes.
Because I'm getting confused here. You originally said that you were doing a load flow on
Yes,
it,
yes.
but by doing the expansion in the 1 over E,
Mm-hmm.
it it seems like the acceleration is now the big term, so that the electric field term is being kept as a big term, in which case it would be the high flow water. What did I miss?
Yes, usually, yeah, this is my notation. Usually, you are playing, arguing about this. So, okay. If we substitute this expression into this equation, okay.
You put an 8 out in front to make it smaller.
Yeah.
Okay.
That's right. And then important fact is that in the presence of stereo symmetry, Boltzmann and the Maxwell equations are invariant under parity transformation, so defined by this. And distribution function, both fluctuating part and answer part should have the same parity transformation. Also, toroidal and toroidal angle component electromagnetic field are replaced by this. And radial component is replaced by minus sign multiplied by this P operator. Okay.
A small question. In the top equation, I understand why the Maxwellian depends on eta squared t. It evolves slowly in time.
Yes.
But the first order part of FA1, in principle, its time dependence would be directly on t instead of eta squared t.
FA1 is corresponding to ensemble average part.
This is all ensemble.
Yeah, so this is not the gyrokinetic equation solution, but the Dorito-kinetic equation solution. Okay. Okay, and also, assuming this kind of expansion, lowest order is completely symmetric with this, then from the uniqueness of the solution, we can expect a complete solution of distribution function and potential having this parity. Okay. Also, if we explicitly expand this function like this, we can say each order of j has this parity. And if we have even number of j, then distributive function is even function and potential function is odd function with respect to the change of the sign of toroidal angles. Okay. So, and also using the stellar symmetry of the equilibrium system, we can say delta j order part of radial transport flux of toroidal momentum vanishes for all even j's. So, 0th order, 2nd order, 4th order, 6th order, 8th order, all components of this kind of pressure tensor related to radial and toroidal directions, and Maxwell stress tensor components related to radial and toroidal angles are vanishing for even j. Okay. And also, if we consider both quasi-symmetric system with stellar symmetry, we already know first order of momentum transport flux is vanishing. That means momentum transport vanishes up to 2nd order in quasi-symmetric system with stellar symmetry. So non-trivial momentum momentum balance equation only appear from the 3rd order in delta. Okay, and using the relation of toroidal flow and radial electric field, 3rd order toroidal momentum balance equation for quasi-symmetric system with stellar symmetry given like this. Okay, and this is so radial profile radial electric field temporal evolution is given by this. And here in the right hand side, divergence of transport flux, momentum transport flux tensor appears. But as claimed by Dr. Kato. Also, if we consider C2 equals 0 case, C1 equals 0 case, that is corresponding to axisymmetric case. So this, so stereo symmetry in the with no dependence of zeta angle. This case, this equation is valid for tokamaks with up-down symmetry. Okay, so if we put C1 equals 0, then this is also describing the temporal variation equation of radial field for tokamaks with up-down symmetry. And usually third order tensor component is not obtained from the solution of conventional order accuracy drift and gyrokinetic equation. I think that is the claim by Whittaker and co-workers.
Can I ask a question?
Yes.
Hare in his talk pointed out that the notion of quasi-symmetry is only good to some order in the helical epsilon. And I think it was third order. So you would, for this to work for a quasi-symmetric device, you would have to have epsilon helical cube much less than delta cube. That seems hard.
Yeah, so here we just assume very complete idealistic
Very idealistic.
quasi-symmetric case only.
This also applies to a tokamak, which is a quasi-symmetric stellar.
Yeah, right. I believe it for a tokamak.
Okay.
Well, so that's a point to ask. Do you agree with this?
Well, that's too schematic to tell you. You got to compare it with under.
But the general order, when you
Right,
when you say third order,
right.
but you and Felix, I thought it had been saying fourth order, or do you mean the same
Well,
thing?
in the pressure tensor, it depends. There's a P3 there that you have to evaluate with moment equations. And if you evaluate it with moment equations, you only need the distribution function of the second one.
Right. In this approach, okay. In this
But
approach,
if you use a brute force approach, then
if you use quasi-neutrality, you'd have to go to fourth order. But in this approach, you just need third order.
Okay, now we move on to the first rotation case. And now we consider momentum balance in toroidal rotating tokamak with toroidal velocity on the order of ion thermal. That is the same case talked by Michael Barnes yesterday. And also, in that case, toroidal flow is proportional to radial electric field like this. And in that case, compare with this flow case, this is third order momentum balance equation for determining radial electric field. But in first flow ordering case, momentum balance equation determining radial field of second order. And also here, toroidal momentum radial flux is given. And that is also using the same technique shown in the previous slide. Toroidal momentum flux is, in this case, second order, and also divided into classical, neoclassical, and honors part too. For example, I'm sorry, it's many quick questions, but in this case, all the second order neoclassical toroidal momentum flux is given by this. And even if we have up-down symmetry in tokamaks, we already lose the invariance with respect to the parity operator in the case of high rotation case. So this does not vanish even for up-down symmetric tokamaks. Also here we need the distribution function of first order that is given by, for example, Hinton 1, that is given by this equation. Also in the right hand side, in high rotating tokamak case, one of the thermodynamic forces given by toroidal flow shear. In other words, that is shear of radial L field. Also, anomalous toroidal momentum flux is also second order in delta, and defined by this using the solution of gyrokinetic equation, non-adaptive part. And here, so also high rotating gyrokinetic equation is given by this, also including the radial flow shear or radial electric field shear. Also, in this the magnetic drift arm, including such as centrifugal force drift terms. Okay. Again, even if we have up-down symmetry in this toroidally high rotating tokamak case, this is not vanishing in second order. Okay. And now we consider quasi-axisymmetric system with quasi-axisymmetric case with toroidal velocity. That is also very close to the Flanders talk. And also in this case, even for quasi-axisymmetry, it is proved that toroidal flow should be given by this and proportional to radial air field. But the important thing, as mentioned by Dr. Henna, we need to consider first zeroth order equilibrium balance equation. In this case, we are considering this case not only this J cross B and grad terms, we have to include this inertia term in the equilibrium force balance. But problem is if we take toroidal component of this equilibrium force balance, we can get this. Okay, simple quasi-axisymmetry case, we just assume that the magnetic field strength is free of toroidal angle. But generally, quasi-axisymmetry case, this is not vanishing generally. That case, problem is radial current does not vanish generally. As well known, in this type of equilibrium, we can never define or construct Buda and Hamada coordinates. So,
this is a good point. I didn't get to this. Just submitted a paper on this, and I heard Steve over lunch. Point is that if you spin up your quasi-symmetric plasma, if you spin up your plasma in a quasi-symmetric center, right, the centrifugal force is not quasi-symmetric. So that
so that is bad news for
the
system. But anyway, so we should be more careful about considering the quasi-symmetric system. It's not totally the same as rigorous symmetric system. So higher toroidal velocity on the order of thermal velocity seem to need additional condition other than simple quasi-axisymmetric condition. Okay. Now,
sorry.
Yes.
Do you need? This is the radial current.
Yes, local radial current.
The local radial current.
And
And if you've got no local radial current, can't have.
Buda coordinate and Hamada coordinate. No. For example, Buda coordinate assume covariant toroidal and toroidal magnetic component is only a function of magnetic surface level. That means
Coordinates assume that, but does that mean you can't construct a set of quasi-symmetric surfaces?
Yes. So if we consider this quasi-symmetric system is always well defined in the case of no flow and toroidal flow, in the zero toroidal flow case, it is natural to consider such a conventional quasi-symmetric system with Hamada coordinate. But we can, we cannot smoothly modify that zero flow case to high flow case by using the same toroidal field structure with quasi-symmetry in Hamada coordinates. That is the point I.
You're just saying that the coordinates don't exist.
Yes. So.
But that doesn't mean you can't find a system.
Yeah, that is a good point. Also, I am not so sure about some compatible conditions for.
But you've surely got to have that the total radial current for a flux surface must vanish.
Yeah, that is true.
Right. But
That is
this
also
is the local radial.
Yes. And all usual of course, magnetic coordinates are, of course, assuming the only balance of these two terms and always assuming the radial current vanish locally. And so I don't know what kind of coordinate should be used for this kind of system. So still, you know, not so sure about the existence of a good toroidal symmetric.
If beta is small, it will be approximately the same coordinates.
Okay.
Yeah, but I mean, there is a condition here, which is the net toroidal, the net radial current through a flux surface.
Also, another point is this is only a necessary condition. We may have other constraints other than this. I don't think only this is vanishing is only the constraint for compatibility of high toroidal flow with chi-symmetry. So we should be very, very careful. You know. Of course, completely.
You still have some kind of quasi-symmetry, you just can't represent it with the coordinate.
Yes. Yeah.
It turns out that you can express the condition of quasi-symmetry in a coordinate-free way, and that's a much better way of we don't need Boozer coordinates.
Right.
There's a more general way of expressing it, which I think avoids some of this.
Okay. Let's move on to the next. Now, interaction.
This was the preface.
This is Alliance large helical device, and this has been already operated for 12 years, very stably. And these are size parameters and maximum plasma parameters. Also, using superconducting helical coils, we have successfully done 1 hour discharge. Okay. And this is showing the classification particles in tokamaks and stellar systems. And in stellar systems, in addition to passing and toroidal trap particle, as mentioned by Hiranda, we have helical ripple trap particle. That is giving rise to the notorious helical ripple neoclassical transport. We also claim, Hiranda claims that this is also very influential on the zonal flow dynamics. For example, left-hand figure is showing the linear eigen function of linear ITG mode, electrostatic potential. We can see this kind of potential modulation in the along the field line that is corresponding to this kind of magnetic ripple. Also, this is the zonal flow response, also in the morning shown by Dr. Hiranda. Also, this gamma oscillation damping and residual zonal flow heavily influenced by the magnetic field structure. This is also later explained in more detail.
But this morning was down to 0, right?
No, not completely zero.
Oh, that's so the residual flow
That's
is
the
time is
residual.
consistent with 1.
Guys, it's the same calculation.
So, yeah, this is the basic equation for pure ITG turbulence and using gyrokinetic ion equation on the Kaji neutrality condition. And here we have shown fluctuations observed in high ion temperature discharging LHD. Left figures corresponding to low TI gradient and right figure corresponding to high TI gradient. And this blue curve is corresponding to temperature minor radial profile. And these are density fluctuation contour on the plane defined by minor radius and poloidal wavelength or poloidal phase velocity. Okay, and in this high TI case, fluctuation peak is more shifted in the core region, and also these are typical poloidal wave number corresponding to the peak of fluctuation. Also corresponding to this equilibrium, Nunang-san, my colleague, calculated using new gyrokinetic protocol GKVX and using the equilibrium data from rigorous BMEC equilibrium data. And this is corresponding, red curve is corresponding to high TI gradient case, and blue curve is corresponding to low TI gradient case. As you can see, this is the minor radial profile of maximum growth rate for high TI and low TI case. And also these peaks are also very good qualitative agreement with the found in peak. Also, these are Florida wave number events of growth rate, and this peak value corresponding to the Florida wave number also good correlation to experimental findings. Okay, so now we consider this fraction may be a candidate of ITG mode driven fluctuation. But nonlinear simulation for these parameters are still in progress and remains as a future task. And now we consider zonal flow and ITG turbulence in this LHD type configuration. And this is corresponding to a tokamak case, and this is tokamak linear gyrokinetic simulation result for zonal flow component. If you give initial perturbation distribution function at having the Boltzmann distribution corresponding to this residual zonal flow level, we can get this kind of distribution function structure. And you can see, we can see this kind of coherent structure in the trapped particle region that is corresponding to neoclassical banana orbit polarization shielding effect of potential described by this. And also this minute structure is corresponding to ballistic style mode, and that is also related to the collisionless damping of gamma oscillation. Okay, and also we have, this is a solution, analytic solution, gyro center distribution function residual zonal flow part can be obtained from the Rosenberg-Hinton theory and given by this. And this is the same simulation result. This is the analytical solution. This is a bounce average, so gamma that's the first scale oscillation are already dropped out in the analytical solution. But we can see very goodly, expressed by the this analytical solution to explain this simulation result. And also, another important thing is this kind of solution is very, very good giving useful information to derive a kinetic closure model. And here, using that kind of solution, we have presented 3 years ago, so closure model. That is a bit different model of V and Hammett, mentioned by Dr. Doran yesterday, but more complicated. But explicitly, such kind of trapped particle structure information enters these parameters. Okay. So and also here, closure is done for parallel heat fluxes, and divided into long time behavior related to residual zonal, also short time behavior related to gum damping, and short time gum damping part is also we used Hammett-Parkin type model, and we have confirmed that this kind of closure model is well described, a good agreement with gyrokinetic simulation result in terms of residual zonal flow for ITG relevant k rho I smaller than 1 unity case. Also, even for ETG relevant k rho E is order of unity case, and this dot symbols are correspond to gyrokinetic simulation, and this smooth line is correspond to fluid model simulation result using that closure model. And transient profile is not so good, but final residual zonal flow level is the same. Okay. And so far, tokamak zonal flow is explained. But from here, we consider collision time reversal zonal flow in helical systems. And in this case, we have analytically derived this kind of response function showing dependence on the initial value, and that is also divided into gamma oscillation part and long time variation part. And the residual zonal flow level is much related to this long time behavior at all. Also, that is very important in terms of turbulence suppression. Low frequency zonal flow is much more effective to reduction of turbulent transport. And in helical system case, as I mentioned before, such helical lip radial motion is giving another shielding effect. And this is giving rise to more enhancement to reduce the residual zonal flow level. And dotted symbol the gyrokinetic simulation and reaching to the prediction of the kind of analytical solution. And this is also showing the comparison between gyrokinetic simulation result about the velocity parallel and perpendicular velocity place. And compared to tokamak case, and these are bounce average analytical solutions. And this provide corresponding to local ripple, helical magnetic ripple bottom, and existence of radial drift of helical trapped particle. And that trapped particle radial motion is given like this oscillated place structure. In this time stage, this kind of dip is found. And this is also well explained the gyrokinetic simulation result, also giving rise to another additional shielding of this residual zonal flow potential. And here, LHC experimental results shown. Experimental data shows for low collisional case, better conformity is observed in the inward shifted configuration where lower neoclassical ripple transport is expected, but more usually unfavorable magnetic curvature driving pressure gradient anticipated. But real experimental observation showing anomalous transport is also improved in the inward shifted configuration. Here we propose kind of scenario neoclassical optimization that is corresponding to inward shifted case with low neoclassical transport, which neoclassical optimization contributes the reduction of anomalous transport by enhancing the zonal flow level. And this is the comparison, linear gyrokinetic comparison of standard inward shifted case. As this is the zonal flow potential time evolution. In the inward shifted case or neoclassical optimized configuration, zonal flow, residual zonal flow potential is a bit higher, but because of bad magnetic curvature, not so different, but the highest growth rate of ITG is a bit higher than for inward shifted case. This is showing the nonlinear simulation result, and red curve is corresponding to inward shifted case, and black corresponding to standard configuration. And as predicted from this linear zonal flow response, in inward shifted case, we have get the higher zonal flow generation, and correlated with that higher zonal flow generation, reduction of chi-I is found. And also this figure shows a very clear zonal flow structure in the inward shifted configuration that is found in the nonlinear gyrokinetic
Do you
simulation.
think that
Yes.
small change in chi,
Yeah.
when you take the 2/5 power, is it enough to account for the factor of 2 change in confinement?
Yes, that's right. So that is next to study our motivation. This is not so big change. I feel the same thing. Okay. That's why we consider, so far, we consider no radial electric field existing in the gyrokinetic model, and worst neoclassical transport is assumed in the previous slide. But real helical system, as explained by Dr. Hernandez, radial electric is given from ambipolarity condition of radial particles in helical systems. And usually that radial electric reduces neoclassical ripple transport. And now our question is how ER influences zonal flow and anomalous transport. Okay, and this is the equation, gyrokinetic equation, as questioned by Dr. Hammett last session. So magnetic field line dependence appear even for flux tube model in the helical system. That is a very complicating ingredient. But yeah, if we consider this omega is corresponding to toroidal rotation speed, and that is acting this part of distribution through this alpha dependence, the alpha denoting the field line ladder. And usually in tokamak system, we zonal flow component have no this alpha dependence, but in helical system, always this kind of magnetic curvature term or Miller force term includes a dependence on alpha field line. That means usually delta itself, even for directly related to zonal flow, delta F has a dependence on field line level, and this equal speed drift very influential on delta F. And therefore, zonal potential phi is independent of alpha. Delta F part of the distribution function comes to depend on alpha. Thus, this equal speed drift rotation influences delta F, and accordingly, zonal flow potential through quasi-neutrality condition. Yes.
What are you using for your other angle variable besides alpha?
Yes.
You only have an alpha derivative with the electric field in it.
Yes.
A derivative along the field line, or?
Yes. So in alpha in special code as a special coordinate, radial in fluxive coordinate, radial coordinate, and alpha coordinate, and the field this coordinate along the field line. Okay. And the radial dependence is just included in this specified wave number vector using bounding
There's
regulation.
an electric field term in there as well?
But
Is in the kr dot v drift has an electric?
okay,
Oh.
This is a linear
This is-
geokinetic equation
Yes.
for describing zonal flow dynamics only.
Right,
yes.
but I'm thinking there are more derivatives when you put in the electric field. Maybe I'm misremembering. Go ahead.
Also, here only constant radial field consider, no shear, background shear of constant. Yeah. Also here we don't consider effect of background electric field shear at all. But even if constant electric field exists in helical case, that is very, very influential. That is the difference, contrasted difference. In the case of
You're taking the electrostatic potential to be a flux function.
Yes.
For lowest order. And
Yeah.
so V truss grad phi or grad psi
Yes.
has components in other directions besides grad alpha, grad D or grad
Yes.
L direction.
So in helical system, in contrast to the case of tokamaks, not so clear decoupling of zonal flow component and non-zonal flow component, even for the linear case. Okay. So in a sense, we artificially defined in this linear problem, phi is free of toroidal and toroidal angles. And using this equation, we calculate delta and combine the.
Look, you better not answer my question. We're running out of time, so we'll talk after.
Yeah,
in
sorry.
detail.
Okay.
I should give you the the official.
Sorry. So in the radial field, if we have no radial field, this is a vertical drift of bounce average drift of helical electron particles are giving notorious 1/nu neoclassic electron. But if we increase resistance, this kind of rotation superimposed and reduce neoclassical transfer significantly. Also, if we have smaller delta E, then that is meaning the reduction of shielding effect of zonal flow potential, and we can expect a higher zonal flow generation by the reduction of radial displacement trap particles. And we skip this. Anyway, using the we have derived anyway this kind of solution. So zonal flow dependence on the initial and nonlinear term. And in the denominator, we have find several contributions from different orbit types, passing particle, toroidal trap particle, or helically trapped particle, and toroidal particle. Anyway,
Numerator, do you have any damping from the turbulence or just driving?
yeah, in this case, collisionless response. And the collisionless case, just if we have no collision, and this linear response only.
What is SIK?
It's like, this is a nonlinear term, so.
Yeah, so that nonlinear term is driving them but not damping them. That's my question.
That is very, very good question. In that sense, this is nonlinear solution too. And
If you have damping.
and also, so in the I think this is not always positive. So I think even if you have this is meaning maybe you are asking no damping, so zonal flow would be increasing monotonically.
It looks like you're doing the Rosenbluth argument with random walk increasing in time.
I don't agree with Rosenbluth argument in that paper. So I believe that this is also divided into generation part and damping part. That's why so stationary state will be kept in that sense. Anyway, zonal flow generation can be enhanced when this kind of polarization effect of neoclassical orbit decreases neoclassical optimization, which reduces the radial displacement or drift velocity. And also, if we have toroidal Mach number, radial electric field increases, this MP, if we have large MP, this denominator decreases and giving higher zonal flow. Also, even if we have same radial electric field, we can increase this MP by using heavier ions. So we hope that kind of changing of proton to deuterium and tritium is giving rise to high MP. Because if we stick to conventional gyro-ball modeling, such isotope scaling in this kind of local flux tube model never expected. So if we do not assume the existence of this kind of radial field, but the inclusion of radial electric field breaks that conventional gyro bomb scale. Okay.
This would apply as well in the tokamak?
But
This would apply as well in the tokamak?
applicability to tokamak, you mean? Not. I don't think.
Only GH? Okay. So
Only GH.
G0.
Yeah. This is not applicable to tokamak directly. And also we have used this is not in order to check that this kind of poloidal rotation by E cross B drift, we need this kind of poloidally global or whole magnetic surface simulation. And Watanabe-san have done by extending that GKB code to the case of poloidally global simulation using many mesh points even for linear simulation. And this is the result. And this no radial. This is inward shifted, and this is corresponding to standard single helicity case. And as you can see, increasing the poloidal Mach number or increasing radial field after gum damping, we can see clear increase. And but the single helicity case not so well neoclassical optimized case. Also, this single helicity case, always the helical trapped particle is also showing kind of poloidal rotation. And maybe this oscillation is related to that. And we have done comparison between gyrokinetic simulation and analytical theory. And this solid curves are corresponding theory and symbols are simulation. And the MP equals 0, as questioned by Gabe-san. If we have no radial field in the limit of 0 radial wave number, the radial zonal field vanishing. But if we have finite radial field, then like a Rosenbluth-Hinton theory, the zonal flow potential amplitude, in the limit of K, that is approaching constant value. Okay. Also, this is another comparison of theory about the Florida Mach number dependence with fixing radial wave number and symbol the simulation and dotted curve the theory, including finite KR effect and non-KR effect. Anyway, at least qualitative agreement is obtained. Now, let's move on to my summary. Okay. And here, fluctuation observed in LHD, high TI LHD discharge are considered ITG modes, predict from linear calculation. And zonal flow response theory and simulation shows zonal flow generation and turbulence regulation are enhanced when the radial displacement of helical rip trap particles are reduced, either by neoclassical optimization of helical geometry, lowering radial trap velocity, or by strengthening the radial electric field to boost toroidal rotation, decreasing the radial displacement of trap particles. Also, ER effect appears through toroidal Mach number, even without no shear of radial electric field. For the same magnitude of ER, higher zonal flow response is obtained by using ions with heavier mass, favorable deviation from gyro bomb scaling. And finally, the momentum balancing equation determines radial field in quite symmetric helical system with stereotypes is shown to be of order of third, and by using Nobel parity operator. Thank you for your attention.